Hello everyone, my name is Xin Huang. I am a PhD student at Hong Kong Baptist University. The paper I presented today is titled Budget Constrained Interactive Search for Multiple Targets. First, I introduce the motivations. Hierarchical trees are everywhere in the real-world applications, such as ACM, CCS, disease ontology, and ImageNet. In the hierarchical trees, the vertex are entities and directed edges are the relationships that a general entity can represent another entity. For example, in the ACM-CCS database, relational database, temporal database, and graph database are entities, and the database can represent relational database, temporal database, and a graph database. Next, I introduce the problem of interactive graph search. There are three important concepts in the problem. First is the target T. It is unknown in advance. In the example, given an unlabeled image, the exact target is dog. The second concept is the interactive questions. To identify the target, interaction is allowed to ask questions. Can X represent the target? If X can reach the target, it will get yes answer. Otherwise, it will get no answer. For example, if we ask an animal, it will get yes answer because the animal can reach dog. If we ask a bear, it will get no answer because bear cannot represent the target dog. Finally, the objective of interactive search is to ask a few questions to identify the exact target. In the example, after we ask questions of pet, cat, and the dog, we can determine the exact target of dog. However, two issues remain open. The first is to identify multiple targets. In real-world applications, an object may have multiple labels. For example, the image have two targets, cat and fish. Another is to identify targets with budget constraint. It takes high cost in the worst cases, so we can control budget that ask at most B questions to find the nearly optimal targets. To tackle these two issues, we propose a KBMIGS problem. Given a hierarchical tree and a set of unknown targets, the objective is to ask at most B questions and then select at most K vertex to represent the targets as close as possible. In the example, we set B equal 4 and K equal 2, and the targets are cat and fish. We first ask a question of pet and get yes answer, because pet can represent cat. Then we ask the object with yes answer, because it can reach one of the target fish. After the questions of wild with no answer, and the fish with yes answer, we select the vertex pet and fish to represent the targets. The distance between selections to fish is 0 and to cat is 1. So the total distance between selection to targets is 1. We call it penalty distance. Then I introduce the related works. The first two related works are IGS and BING. Both these two related works study the interactive graph search for single target and without budgets, so it may ask lots of questions in the worst case. Another related work is HGS. Different from IGS, BING, and our work, HGS is an offline method which asks all the questions in one run. Another weakness of HGS is that it takes a high time complexity for multiple targets. Next, I introduce our algorithms. To tackle the KBMIGS problem, we first propose a framework which can be applied on both single target and multiple targets. The key idea is to select a vertex with maximum expected gain to ask a question. In the hierarchical tree, the top vertex, such as V1, always has a high probability to get yes answer, while high gains to get no answer. For the bottom vertex, such as V6, always has a high probability to get no answer, while high gains to get yes answer. So to balance the probability and gains, we propose the expected gain function. PS and P0 are the property of vertex to get yes or no answer. Yes and no gains are penalty distance reduction after vertex gets yes or no answer. Here, penalty distance is the minimum distance between the best selection in yes candidates and the potential targets. And the yes candidates are the vertex can reach the targets after questions, and the potential targets are the vertex may be the targets after questions. Next, I show a running example of single target search algorithm. Here we assume the target is V5 and the budget B equal 2. The initial yes candidates are V0 because it can reach all vertices and always get yes answer. Initial potential targets are all vertices. First, we calculate PSP node, GSG node, and the expected gain of all vertices. We ask a question of V3 with max expected gain and get no answer. We can prove V3, V6, V7, and V8 from potential targets because these vertices cannot be the targets. The yes candidates will not be updated because we get no answer in this question. For second question, we update the expected gain and select V5 with max expected gain to ask. It gets yes answer. So we can add V1 and V5 into yes candidates because they can reach V5, which gets a yes answer. For more, only V5 and V9 are still potential targets because in a single target search, the target must be the descendants of yes candidates. After asking two questions, we use the best vertex V5 in yes candidates as a selection. Note that in single target search, the best selection is always yes candidates intersect potential targets with theoretical guarantee. Next, I introduce our multiple target search algorithm. Similar to the single target search, we apply the KBM-IGS framework by selecting a vertex with maximum expected gains to ask. Different from single target, it is challenging to calculate planetary distance in multiple target search because here we select the best K vertex and K may larger than 1. To tackle it, we propose a dynamic program-based algorithm, KBM-DP. Next, I show a running example. Here we assume the target is V5 and V8, budget B equal to and K equal to. First, we ask a question of V3 with max expected gain and get yes answer. Based on it, we update the yes candidates potential targets and the expected gains. For the second question, we ask V5 and also get yes answer. After asking two questions, we select the best two vertices V3 and V5. Note that, different from single target search, we apply KBM-DP algorithm to select the best K vertex optimally. Finally, I conclude our algorithms. First, we propose a novel KBM-IGS framework. Based on the framework, we propose STBIS algorithm for single target search and KBM-DP for multiple target search. To improve the efficiency of KBM-DP, we propose two heuristic algorithms, KBM-TOP-K and KBM-DP+. KBM-TOP-K is an algorithm that varies gain function to improve efficiency of gain calculation, and KBM-DP+ prone disqualified vertex to save computations. For details, refer to our paper. Next, I introduce the experiments. We conduct the experiments on Cocoa ImageNet and Yago. In the image Cocoa and ImageNet, the ground truths are the images with multiple labels in the net, and in the Yago, the ground truths are the entities with multiple types extracted from Wikipedia. We compare our method with HGS, IGS, and BING, and we set the default budget as 50 and K as 3 for multiple targets. In the quality evaluation of single target, our STBIS method outperforms the state-of-art algorithm with the smallest penalty in most cases. In the quality evaluation of multiple targets, our method outperforms state-of-the-art algorithms by achieving an average of 2.1 times better results. In the efficiency test, our fast heuristic algorithm KBM-TOP-K and KBM-DP+ were much faster than KBM-DP, and KBM-TOP-K is competitive with BING. Finally, I conclude our paper. We studied the problem of budget constrained interactive search for multiple targets. To tackle it, we propose a novel KBM-IGS framework. Based on the framework, we propose STBIS algorithm for single target and KBM-DP for multiple targets. To improve the efficiency of KBM-DP, we also propose two heuristic algorithms, KBM-TOP-K and KBM-DP+. Thank you for watching.